Howdy folks, this is my version of Pandemic Learning of Volume. First I want to start with some very basics, which is a demonstration of the actual shapes of the 6 main types of questions you're going to see. So I'm going to hold them up. Well, actually, I'm not going to hold, Anna's going to hold them up for you. Let's start with the cube. Number 1, yes. So note the shape of the cube. I want you to note that all of the dimensions are exactly the same. The length and the width and the height. Stick your hand in the hole so you can show that it's three-dimensional. Okay, we're going to put some water in that later. Now the next one I want you to do is a pyramid. So upside down so you can see that. Okay, there's your pyramid. Now notice the shape of the pyramid on the bottom is exactly the same shape as the cube, but it has walls. They don't come to a straight up, they come to a peak. That's a pyramid. You can have pyramids, by the way, that are rectangular on the bottom as well, not just square, but what we're going to deal with here is a square bottom. Ooh, nice work, Bitsy. All right, now the next one. Let's do the cylinder. So a cylinder, as you will recall from grade 3, is a circle with walls. Think about a can of soup. Okay, and all those you that are on pipe fitting, that's going to be typical for pipes and for tanks and so on. Okay, now let's compare that to the cone, actually the other guy. Note flip the cone on its edge towards the camera. Notice at the bottom of a cone, flip her 180, flip the other way, is a circle. And it also has walls. But the walls don't go straight up and down like in a cylinder, they meet at a peak, such as the perimeter, or the pyramid did rather. So keep those in your mind for comparison's sake. Now we have, let's do the, what's called the rectangular prism, the box. Now this one's a little bit different. Show the open there. So we have a length and a width and a height. Three-dimensional, it makes your typical box. Okay, and that's called a rectangular prism. And last but not least, we have this sphere, known as a sphere. Not a spear, like you should be within the 1700s, but a sphere. There's only one dimension in a sphere, and that is a distance from the center to the outside edge, or from the center to across the middle, like the diameter basically. Okay, 6 shapes, you need to know those. Another little section of this experiment we would do if we were in school would be, I'd ask you in your team to look at the bottom of each of these shapes, the open side, and tell me the shape. So although this is a three-dimensional cube, the open face of this shape is actually a square with walls. Now let's show the pyramid next. The open face of the pyramid, you will note, is a square with walls that come to a peak. Now the cylinder is, the open face of a cylinder is, oh my God, a circle with walls that come straight up, compared to, Vanna White, you're awesome. Do this cone next. The cone. The cone is also a circle with walls, but the walls come to a peak. They don't come straight up. And lastly, there is no, oh, I forgot about that guy. That, you know, you're right. That is a rectangular prism. The bottom of this one is a rectangle, say a length and a width. And then it has a height, about finger width in this particular case, about 10 centimeters. Now the sphere has no open face. Keep that in mind. To do something different with that after, to explore the formula of such a thing. Okay. So here we have a cube and a pyramid. Examine the base of the cube and the base of the pyramid, and I want you to notice they are something. What do you see? Okay, think about that. Now we're going to fill the pyramid with water, and we're going to pour it into the cube. Okay, that's full. Now the question I want you to look at is, are the volumes equal? I think you can see that the cube is not full. How many times do you think it would take of pyramids? How many full pyramids do you think it'll take to fill that cube? That's our experiment. So watch and see. Not full. Full, not full. I want you to make a mess. In the classroom, there's water everywhere when we do this. Okay, that's just because it wasn't quite full the second time. But notice it takes, minus human error of the helper, it takes 3 full pyramids to fill the cube of the same dimensions. This next little mini one is a comparison of the cone to the cylinder. So notice the base of the cone and the base of the, move them around a little so you can see full 3D dimension a little better. Make the walls more visible. Hold it upright. Upright, completely like so that, yep, and the cone as well beside it. Notice it is same dimensions and height, and it's the same bottom. So I'm gonna ask you the question. Make a prediction. Let's fill the cone and see if the cone volume is equal to the cylinder volume. And I know you're not stupid. I know that you know the answers are going to be, they're not equal. We're going to fill it like we're going to make business. You're a wimp. Okay? See, you got half it up the side. There you go. Now go big or go home. So 1 didn't do it. 2 didn't do it. Fill that sucker, will you? Fill it to the max. Oh, that's good. Oh, that was excellent.
That was dramatic.
And that's, of course, you can see, besides our human error effect again, that would be perfectly 3 full cones inside of a cylinder of the same circular bottom and the same height. Okay, our last little mini investigation is looking for a relationship between the sphere and the cylinder. So in the classroom, the sphere is kind of not particularly well put together. As you can see, it just fell apart. So the students tried to tape it up and they try to fill it, and it's usually a very big mess, and it's quite hilarious. So predictions first, I'd ask for predictions, and they would say that they think 1 sphere is going to fill the cylinder. So I suggest that they take the sphere apart and they fill a half of a sphere twice into the cylinder and see if that fills it. So let's experiment with that. So that's the equivalent of 1 whole sphere. You'll notice that it doesn't fill the cylinder. If we put 3 spheres into the cylinder, we would definitely have too much water. But, so you want to do a sphere and a half, is that what you're saying? Go ahead, try that.
A sphere and a half.
A sphere and a half.
Okay.
We'll see what happens. Would you look at that? A sphere and a
No
half.
human errors.
No human errors. Beautifully done. Now I want you to take the water in the cylinder and dump it into the cube. I want to do one more thing. So we have that empty. Now I want you to see the relationship between the cone and the sphere. So can you fill the cone with that, do you think? Some trees and
I
bugs.
think so.
Let's see what you can do. A cone. No. No. Okay, that's okay.
Oh.
Okay, fill it again. Keep filling it.
Which one?
The cone.
The cone. Okay.
Okay, now I want you to fill the cone with some water. Okay, now I want you to put down the cube. Pick up the sphere. And I want you to hold the sphere over the cylinder just for protection. And I want you to take the full cone and pour it into the sphere and see what happens. Would you look at that? A cone is the same capacity, the same volume as a sphere with equal dimensions of a diameter. Keep this in mind. We're going to have a good lesson on this during our next class. And what we have here is a little kit that I bought off the old interwebs to demonstrate volume in measurements that are not necessarily lengths and widths, but in liters or a capacity. This big block here in front of me, I want you to notice that it's 10 units long, and each of those units is a centimeter. And it's 10 units wide, and it's 10 units deep. So down the other way, down the side, yeah. So let's top, so lay it flat on the table for a second. So the top of this shape is 10 by 10. So you can see the top has 100 squares. When you make that shape 3D and you add walls, the walls are also 10 centimeters tall. So in total, this cube is 10 centimeters by 10 centimeters by 10 centimeters. The math says there's 1,000, hold the little one, there's 1,000 of these little 1 centimeter cubed or 1 cubic centimeter blocks inside the big block. And the most important thing that I want this little video to demonstrate is that if the big blue block was hollow and we filled it with water, that's the exact equivalent of 1 liter. So I want you to memorize from here till the end of time that 1,000 cubic centimeters, or a block, this is not a very big block, you can hold it in your hand, 1,000 cubic centimeters is equal to 1 liter. Okay, and the little cube, which is a centimeter cubed, is in fact equal, that's cool, you can do, yeah, it's really cool, that's a good way to demonstrate it. That would be the grand total of 1 milliliter. So if you had 1,000 those little cubes, 1,000 milliliters equals a liter. So when you're asked to do conversions to milliliters for your final, for liters in your final volume, you should think about changing your dimensions to centimeters first, because you will now have this magical conversion that says 1 cubic centimeter is equal to 1 milliliter, or 1,000 cubic centimeters is equal to 1 liter. Just stew on that for a little bit.